Alright, welcome back guys. This is the second class in the class of 3 series that we're going to be doing. If you weren't here last week, then that's okay. 如果 last week 你没有来，没关系, we can still continue. We may as well get started because we have a long day. First of all, I want to make sure, does everyone here have access to MATLAB? Put your hand up if you can't get MATLAB. Does everyone here have access to a C compiler? 因为如果你现在没有办法写 C 还是没有办法写 MATLAB, 最好你回家. Best to go home now because we're all going to be writing C and we're all going to be writing MATLAB together. All today. 所以我讲的时候，如果你还没有安装一个 C compiler, when I'm presenting, I want you to be installing a C compiler. 其实有很多免费的选择 if you haven't got one ready. If you are ready, then we can start. Wonderful. So welcome back to our Nano-Course. Everyone should know who I am. My name is Matthew. Chinese name is Li Wenhua. I'm a professor at NTKU in mechanical engineering. In case you missed the first part, if you weren't here last week, I see some new faces. All we did really was derive the finite difference representations for the heat transfer equations. Then we took those discretizations and we solved a 1D and 2D problem. During class, I showed everyone last week how to solve a 1D problem using MATLAB, and then I gave you a challenge question to solve a simple 2D problem. If you had trouble doing that, that's okay. I can give you some code today to let you catch up. If you weren't here last week and you need some code, come and see me. Today we're going to be using MATLAB and C, but we're not going to be using the same solution scheme we did last week. Last week I showed you guys how to solve explicitly, using an explicit technique, solve the motion of heat accurate in time using the FTCS method, the forward time centered space technique. Here is a code that we developed last week for 1D in MATLAB. So it's actually quite neat. Last week I asked everyone to write this down. In case you need it, here it is. So if you need another copy, you can come see me later. The key concept was that the FTCS technique, that's a finite difference technique, is designed to solve the transient heat transfer equations explicitly. That means we find the time accurate solution to temperature based on the old temperatures in the previous time step. So the temperature at time k plus 1 is based on the temperature at time k. All of our computations for temperature use the old values. And this is because our finite difference representation, in our finite difference representation, we took the gradient terms on the right hand side of our heat transfer equation and we used solution at time k to get those, to approximate that derivative. In this method, in the explicit technique, we saw that we needed to limit our time step, that's dt here on line 7, to maintain stability. During last week's course, I asked everyone to set dt to be 1 by 10 to the negative 4, and we found out that after one time step, this solution technique became unstable. And that's a problem with any explicit finite difference scheme. You need to use a very small dt to get our solution. So this means that we had to change our dt to 0.25 by 10 to the negative 4. And then our simulation ran. So when we ran our codes last week, this was the first result I asked you guys to do. We set dt equal to be 1 by 10 to the negative 4, and we got this unstable result. That's with our CFL equal to 1. Then we asked everyone to change dt to be 1/4 that size. So the CFL went to 0.25, and a single time step gave a stable solution. So we know unstable, stable. And this is a big problem with FTCS, a big problem with any explicit scheme. When we use explicit schemes, we need very small dt's. Some people find this problem to be so large that they don't like to use explicit schemes, and there are other ways. And that's what today is about. In the previous class, we looked at FTCS, a forward time centered space method, and we have these two derivatives. We have a derivative in time, and we have derivatives in space, second derivatives in space. And we needed to find a way to use a discrete form to approximate these terms. So on the left-hand side, we used a backward difference or a forward difference? You guys can decide. It must be, forward time, right? Since it's called FTCS. So that's a forward difference for our time derivative. And for our space derivatives, we use central differences to approximate, to discretize that continuous term. And so here is the entire equation, but what we can see is, here we have a forward difference of temperature and time. Here, all of these spatial gradients of T were evaluated at time k, so we used the old values of temperature to approximate these. There's no reason why we had to make this choice. It's completely up to us. If we want, we can choose to evaluate these guys at time k plus 1. But if we do that, then we have a problem, because it means that we have an equation in terms of the temperature at time k plus 1 related to all of the other temperatures at time k plus 1. So we can't solve them one at a time in an explicit fashion. So let's have a look. Here's what we did last week. We looked at a 1D problem, so all of the other guys disappeared. In the challenge question, you guys did 2D, but at the beginning we looked at 1D, and we evaluated this guy using forward difference, this guy using center difference, but all of the k's here are k. These are old temperatures. Here's the new temperature, k plus 1, here's the old one, divided by dt, that's our temperature gradient in time, and here's our spatial gradient, all in time, k. And that's not going to cut it anymore. We made an arbitrary choice to evaluate that gradient at time k. Instead now, we're going to attempt to evaluate it in terms of the temperatures at time k plus 1. So the left-hand side hasn't changed. We're still t of k plus 1 minus t of k. That's the same. That's still a forward difference. But on the right-hand side, you can see the form is still the same. We still have t to the left, or t to the right, plus t to the left minus 2 of t in the middle. But all of these k's are k plus 1. They're based on the new temperatures. Now, the previous week, we preferred to use time k because it made the equation for time at k plus 1 very easy. It was just a straightforward calculation, a straightforward equation. But now, we need to solve for t at k plus 1. We have 1, 2, 3, 4 temperatures at k plus 1. We have t of k plus 1 at ij here, t of k plus 1 at ij here, and t of I plus 1 and I minus 1 at k plus 1 here. So we can't solve for the new temperatures one at a time. We have to solve them all at the same time. And when you have to solve a set of unknown equations simultaneously, that means we're going to have to solve a system of simultaneous equations. So we're going to have to solve simultaneous equations, a system of equations, which means we're going to be working with matrices, basically. So let's continue to move forward with this discretization. What we have here is the equation I just showed you. What I want to do is arrange it in terms of all of the separate tij's. So I look at tij and ti plus 1j, ti minus 1j. So we separate all the terms. We collect all of the tij's. This is the intermediate step in case you're wondering about the math. What do we do here? This dt goes up here. So we have a term here. dt times theta divided by dx squared, that's the CFL number, right? From last week. For an explicit technique, we needed to keep this less than 0.5. But it's going to become unimportant in this class. So we've got a t of k plus 1 here at ij. We've got negative 2 of them here. So we want to factorize these out. So we have t at k plus 1 ijk, 1 plus 2 dt theta divided by dx squared, because this negative and this negative turn into a positive. So we have this term here. All of the other guys, we have negative dt theta dx's, or negative t times positive those. So we have coefficients here for each term. Equals to t of k. So now what we have is the old temperature t of k. He's by himself. We only have a single temperature from the old time step. Only the time at ij. Only the temperature, sorry, at ij. He moves over to the right-hand side. And he's by himself. He's going to become a source term in our matrix problem. So let's have a look. We can actually write this in matrix form quite easily. You can imagine. We've only got 3 variables here. T at I minus 1, k plus 1, t at I, k plus 1, and t of I plus 1, k plus 1. We have, this is the main term, our I term. So if we have a matrix, this is going to be our diagonal. This is the guy to the left, and this is the guy to the right. So we can recompute. The temperature at the old time is basically a combination of these temperatures at the new time. Now we want to create a linear system of equations based on this concept here. So what we need to do is, after we have a large number of t's at different locations, we're going to have a large square matrix here and a single vector of all temperatures here. Let's have a look at what that will look like. So if we have a large ax equals b system, let's do some math on the blackboard. Oh, this pen doesn't work very well, does it? Let's try this one. Excellent. So we're going to try and solve the temperatures at T1, we have a long 1D problem. We have T1 here, T2, T3, some Ti here, all the way up to T of n. We're going to solve all of these, T2, T3, all the way up to Tn. And we're going to have a matrix system to do it. This I'm going to call A, this is my x, and this is going to be a vector B. This is going to be all of the temperatures at time k. The all temperatures. That's what it's going to look like. This vector here, our x vector, those are all of the temperatures at our new time. That's our mission. We're solving for these. And this A matrix is going to be a large, sparse, diagonal system where all of the diagonal terms look something like 2 dt theta on dx squared, all like that. Oops, that's a dt theta on dx squared, all the way down here. And on the off diagonal terms, we have these negative dt theta divided by dx's. So we have a symmetric matrix. That's very important. The matrix is positive definite. That's important too. So we have a symmetric positive definite matrix, which makes this matrix about the friendliest matrix you're ever going to see. So it's a nice matrix to solve to start with. That's what it's going to look like. So all you need to remember is that the diagonal terms look something like this. And the off diagonal terms to the left and right, it's a 1D problem. So we have a relationship between the temperature at I and I plus 1 to its right neighbor. That's just going to be negative, it's right here, dt theta on dx squared. And here's on the left hand side, negative the same thing, dt theta on dx squared. It's funny, all of the non-diagonal terms are just a CFL number, negative CFL. And on the diagonal terms we have 1 plus 2 of the CFL numbers. So it's funny, we can construct A from the identity matrix and then add some CFL numbers into the equation, and that gives us our A. It's got some very curious properties, this guy. However, if we just build it like this, we still have the same problem we had last week, boundary conditions. You might remember from last week using FTCS that the boundary conditions were very, very important. We basically have two kinds of boundary conditions, right? We have, last week I talked about them, we had Newman, that's a zero gradient or a specific gradient, and we had Dirichlet, where you set the temperature to be whatever you like. Let's talk about Newman at the boundary. So if you have a Newman condition, you might remember from last week's. If you weren't here, I'm going to tell you now anyway. So we have a cell here, that's a point at Tn. Here's real. Here's contained within our solid object. Out here we have space, nothing. We need to insert what we call a ghost cell here. This is a ghost cell. And we need to have a temperature Tg. If we want the flux of heat to be 0, if we're going to use a Newman condition, remember the flux, that's equal to negative k times dt dx. We want this to be 0, so we have negative k. dt dx is going to be T ghost divided by Tn, the inner one, all divided by dx. That's approximately our flux. If we want this to be 0, that means that Tg must be equal to Tn. So the temperature on the outside, on our fake point, must be equal to the temperature on the inner point. What does that mean for us? Well, our original equation, let's have a look. Let's see. We have two of these, right? If one of these is equal to this guy, one of those terms is going to disappear, and this is going to reduce by 1. So let's have a look at the final governing equation for this when we write it in implicit form. We see we have a temperature at I plus 1. This is the time derivative times by dt. The Td is gone over here. But we used to have negative 2 times T of k plus 1 at ij. One of those is gone. And the temperature at Ti minus 1 k plus 1 is gone too, because we set that equal to. So in this equation, we're looking at the temperature on the left-hand boundary. So the equations change a little bit, and instead our diagonal term goes to 1 plus a single dt theta divided by dx squared. The right-hand guy is still there. In this equation, 我们是看最左边的 point. 如果我们是看最右边的 point, 大概是一样, but this guy will be I minus 1. So the second term will be at I minus 1 and not ik plus 1. So that means our matrix will change. 如果我们有那个 Newman condition, let me change the color of the pen. For a Newman boundary, this right-hand term, oh my goodness. This pen needs to retire. Thank you. Does this pen need to retire too? Okay, he's good. dt, that's a dt, paise, divided by dx squared. So there's only one of these here. And this guy here would normally be 1 plus 2 dt theta divided by x. 它会变成一样. He's going to change to one of them as well. So we have to change, wherever we have a Newman condition, we have to change this from 2 to 1 of them. 其实如果你忘记的话, you just need to derive the equations again and you'll see. It's actually quite straightforward. If you get stuck with this, you can always ask me for help. So that's what our A matrix is going to look like. There's our boundary condition. So you can see here, for this problem, it's a 1D problem. My A matrix is going to be very large. I haven't written all of the points in. All of the middle rows here are going to be the same. But on the left-hand side, we have a Newman condition. So I set, you'll see there's only one dt theta divided by x squared. Down here, you can see I've also used a Newman condition because there's only one dt theta divided by x squared there. All of the others are 1 plus 2 dt theta divided by x squareds. And to the left is the same thing. Negative CFL on the left, negative CFL on the right. So this matrix is quite easy. We know it's positive definite. It must be symmetric. 哎，我问你一下，如果这个 matrix 是 symmetric， 这个真的是什么意思？ What does this really mean physically with physics? It means that if you have heat moving from this end of the bar to this end, the physics of the heat moving this way 应该是跟 the physics moving this way 一样。So if the temperature here is 10 and the temperature here is 1, the solution must be the same as if the temperature here is 10 and the temperature here is 1. Because if you turn it around and look from another angle, the direction changes, but the solution doesn't change. So the solution has to be insensitive to your coordinate selection. That's why this matrix has to be symmetric. If it's not symmetric, it must mean that the temperature flow in one direction is different to the other direction. In real life, this happens in composite materials and semiconductors. So if you have a special material that doesn't allow heat to flow the same way in all directions, your A matrix may not be symmetric, which is a problem because if you're going to simulate heat transfer using an implicit technique, that means your matrix suddenly is not symmetrical and you're going to have to use a solver that handles non-symmetrical terms. But for today, one-time special deal, we have diagonal terms here of the CFLs. The matrix is sparse, positive, definite, and very friendly. How do we compute the new temperature then? Well, all we need to do, on the right-hand side we have our B. These are our old temperatures. Here is our goal. We're solving for this. Our A matrix, does this change with time? No. All we have here is the CFL number. So for any simulation, 如果我们的 simulation 我们的计算那个 CFL number 没有改，那我们的 A 没有改。That's really great, 真的很方便. Because the solution at k plus 1 is the inverse of that A matrix times k plus 1. So if you want to find the next temperature, take the inverse of this, multiply it by the old temperatures. Then that gives you the new temperature. Then if you want to find the newer temperature, you take the same inverse and you multiply it again by that new temperature vector. And you just keep getting the new temperatures by multiplying that A matrix, A minus 1 matrix, sorry, by that old temperature vector. So a piece of cake, because 那个 A 没有改变，我们只要算一次而已. We compute A minus 1 once, and we use the same A minus 1 over and over and over again to get our transient solution. So in a little bit, I'm going to show you my MATLAB code. Not now, soon. 我会给你看我的 MATLAB code, 你会发现最困难的就是 making this A matrix. 最简单的, the easiest part is solving for the new temperature. It's just one line. T equals INV inverse A times T. Win. One line. 就成功了. Creating this A is not one line. That's a lot of lines. And if you're using C, it's going to get worse. The good news is, if we're going to compute A negative 1, we only have to compute it once. But the other problem is no one likes to compute a negative 1. Because if this matrix is sparse and it's n by n, I promise you a minus 1 is not sparse. So you're going to have n by n of a lot of things. So A is easy, but a minus 1, not so easy. You're going to run out of memory very quickly in MATLAB. You'll discover if you use too many cells in your problems. You're going to find out in the challenge question. But this is how we compute the transient solution. So this way we can use an implicit technique, solve for all of the new temperatures at the same time, not one at a time, not like FTCS. And then we can compute the new temperatures at any time by using the same a minus 1 over and over and over again. So that's how we get the transient solution using an implicit technique. That's a transient solution. So that's where we have a single dt, and one with the t at k plus 1, 真的是 the solution at time t plus delta t. So that way we can track our solution in time. 所以这个如果那个你跟那个公司合作，他们是教你 find the temperature at 5 minutes， 那你一定要用类似的算法。You have to use this technique. 如果他教你说 find the steady solution， 我没兴趣看那个 intermediate solution. I only want to know the end solution after time equals infinity. Great, we can do that. If we have, let's write our full equation out. Again, 这个是 1D equation. This is a discrete form using finite differences. 我跟你讲 finite volume and finite element give the same equations. If you're interested, I can show you later today. For steady, what will this guy equal to? The first derivative here is the time derivative. The change of temperature in time. If we have a steady problem, that means the rate of change of temperature in time is 0. So we can kill him. You can buy a gun and shoot it. You can't buy guns in Taiwan, right? So you might just have to delete it using an eraser or something. Much more peaceful solution. So we neglect this. Now if this is gone, we have this guy equals to 0. What happens to that dx? Well, we can kill him too. There's a 0 here. There's no source terms in this equation, so he's gone. Theta, he's gone too. So we find that the new equation is only a function of temperature. We find in general, the general solution to a heat transfer problem in a homogeneous media is independent of the media and independent of space, if your grid is evenly discretized. So we have an equation for the 3 new temperatures, only the 3 new temperatures in terms of 0. So the steady solution is independent of theta and dx. Is this a good thing? Yes and no. The good news is, see this A matrix here? If you were to work out the condition number of this matrix is a function of your CFL. If you have a tiny CFL number, I can tell you the condition number is going to be quite small. If you have a 100 mesh from 1 to 100 and you have an A, that's also going to be 100 by 100, and your CFL is 0.25, your condition number is 2. 2.0. Win, that's a very low condition number. That means it's extremely easy to solve. This guy, no CFL in him, you'll find that if you have a 100 by 100 mesh and you write your equations like this, you create your A matrix without CFL, just with these guys here, your condition number will be like 40,000 for a 100 by 100 system. So we'll come back to this later. First of all, we have another fire to put out. So let's consider the same problem. We have a 1D bar, we have a Newman condition at the left end and a Newman condition at the right end, which means we lose one of the 2's here and here. All the rest are 2, 2, 2, 2 with 1 on the left, 1 on the right. 所以其实跟这个差不多, right? We say that this guy is going to be more dominant than this guy. 我们也可以说 in steady 就是 t equals infinity, right? So for t equals infinity, we have 2 of infinities here, minus 1 infinity here, minus 1 infinity here. So we can see this little 1 here is dead in the steady limit. So we get this matrix, but we have 1 here and 1 here. What's the determinant of this matrix? I'll give you a clue. It fails the Wronskian test. What does that mean? You guys learn Wronskian? If you say Wronskian in Russian, you have to say Wronskian, like that. That's the real way. Because Wronskian was Russian, right? He was Russian. The Wronskian determinant is 0. That's bad news, isn't it? If the Wronskian determinant is 0, if the determinant is 0, that means the Wronskian test for linear dependence has failed, which means this matrix is singular, and you don't have a solution. 应该是说 you have a billion solutions. That's the problem. If you have a Newman condition here and a Newman condition here, how many solutions do you have for this steady result? An infinite number. If you have free heat flow here and free heat flow here, any linear solution is going to be a solution to your equations. So there's not any single solution. We have an infinite number of solutions. So for steady simulations, we can't set Newman conditions on every boundary. This is exactly the same as if you try to solve a PDE properly, analytically, and you only employ gradients of the first gradient in your solution. If you don't set one of the solutions, one of the boundaries to be a real number, use a Dirichlet condition, if you try to use Newman conditions at both ends, you're going to fail. There's no solution. It's singular. Oh, if you get stuck here, you can ask me for help later. But the easiest way to prove this to yourself is to load this into MATLAB and type CONDA. And it will say the condition number is infinity, which means it is infinitely hard to solve, which means there's no inverse. Or you can find a determinant, DETA. It'll be 0, I promise you. So that's bad news. The reason is the selection of boundary conditions and the simple fact that the initial condition, which controls a steady state solution, does not play any role in the equation. Did you see that? If we have this guy, remember we have these equations here. Right hand side is 0. They're all gone. We have this internal point here. We have nothing on the right hand side. Nothing. So where does the initial condition come into play? Nowhere. So this matrix doesn't know what the initial condition is, and you tell it to put Newman on the left, Newman on the right, there's no way it can tell you the answer. It's impossible. You don't know how much energy you had at the start. So for an example, to be very, very specific, let's have a look at the transient problem. Here is space. Here is temperature. Last week we examined this solution, right? Where the temperature is 0 and temperature is 1. We used Newman conditions on both sides. We were able to find that the steady solution was this, at half, t equals 0.5. And can you shoot this pen, please? Yeah. Here. I'll hide it here so that I'll never see him again. He won't be back. All right. So we have t equals 0.5. If we set the initial temperature to be like this, so here this was x equals 0.5. If we have x equals 0.25, so we have 1 here and 0 here, the steady solution is going to have to be us sharing all of this energy evenly across the entire flow field. What's it going to be? A quarter? Everywhere? Does that make sense? So we have 1 energy times a half is the total energy, then we divide by 1. We have 1 temperature times by 0.25, then we divide by 1. The steady solution is then going to be 0.25 everywhere. Right? That's a steady solution. So the steady solution, if you have Newman boundaries on the left and right hand side, the steady solution is 100% a function of your initial condition. In this matrix, our initial condition is not anywhere to be seen. It's gone. So to find a steady solution in this way, we need to use a combination of different boundary types, Newman and Dirichlet types, in order to prevent the A matrix from being singular. If you were to change this 1 to a 2, that means you've got a Dirichlet condition on the left-hand side, and your matrix is no longer singular. Very convenient. If you change this 1 to a 2, the matrix is not singular anymore. Its determinant is not 0. Oh, you can check this yourself. Let's have a look at the example. We've got a 1D problem from 0 to L equals 1. We're going to set the temperature on the left-hand side to be 1 and set the temperature on the right-hand side to be 0. 如果我们这里的temperature是1 and 这里的boundary condition是一个 Newman condition, What's a steady state solution? Let's think about what that means. We fix 开始的时候不管那个 temperature 是怎么样 it's not important for this problem. If you have a 1D bar and you set the temperature at the left end to be 1 and no heat comes out the other side, that means heat is going to continue to come in until the temperature is 1 everywhere. So 如果这个是一个 Newman condition, 那你的 steady solution 就是1 everywhere. 如果你开始时候这个 temperature 是 0.5 and is fixed at 0.5, that means your steady solution will be 0.5 everywhere. So in this case, your boundary conditions dictate what your solution will be. 如果 we don't use Newman on the right hand side, if we keep this a Dirichlet condition, set t equals 1, t equals 0, the solution to your differential equation, your heat transfer equation, must be a straight line going from 1 to 0. So if you have any heat transfer problem, this is actually a very good rule. If you have a heat transfer problem and you know the temperature here is X and the temperature here is Y, the steady solution must be a straight line connecting the two temperatures. So if someone in industry gives you a horrible geometry, something really disgusting, a jet fighter or something, an engine, and says, find me the steady temperature, and you look at the initial conditions, the boundary conditions, and you know the temperature there is 5 and the temperature here is 0, you know the solution must be 2.5. If there is a straight line and no other complicating factors, like non-homogeneous materials or something like that. For easy things, we know it's a linear relationship. So if you solve this system, these are 2's and 2's because we're using a Dirichlet condition, so you don't take away one of the points here. So we have 2 along the diagonals, negative 1's on the off terms. This determinant is not 0. If you find the inverse of this, what we have here, B, the temperature on the left-hand side, 变成一个 source term. Sorry, let me explain why. So what was the governing equation? There you are. There's a solution. There's the explanation why. We used to have negative t of I plus 1. Hang on, is that negative? Have I made a mistake in my slides? That's meant to be positive 1. That's what we call a typo. If you copy this slide, you're going to get negative 1 as your temperature at the left-hand bound. That should be positive 1. So the temperature on the left-hand side of ij, that's I minus 1j, it should be on the other side as negative. You ship it over to the other side. It's constant now. It's fixed. It's a Dirichlet condition. We set it to be 1. We're not solving for any more, so it's a source term. So you can see on our B vector, our laser, there we are. This B vector is going to be a long vector. In this case, the only non-zero vector will be the first one. It's going to be fixed at 1 because that's our temperature. The very last one is 0 because our temperature there is 0. Convenient. If the temperature here was 0.5, the last term of B would be 0.5. The rest of B is 0. So that's actually a really nice system to solve. So in the case where we have geometries where the diffusivity, the thermal diffusivity is constant in space, and all of the grid points are nicely evenly distributed, the A matrix and the B matrix are actually very easy to build and store and solve. A diagonal system like this is a piece of cake. In which case the steady solution is simply the inverse of A times B. Again, where B this time are the temperatures at your boundary conditions. So for unsteady heat transfer, your B matrix is the old temperatures. For steady heat transfer, your B matrix are the temperatures at the boundaries. That's basically it. So we can summarize now. For unsteady implicit heat transfer, you have this A matrix, which is basically the same as this one, but all of the terms here all of these numbers here are attached to CFL numbers. So we have 1 plus CFL along the diagonals. Sorry, that should be 2. That's a typo as well. I cut and pasted too quickly. So that's 2, 2. No, pass it. I did not make a typo. That's right. 1, 1, 1, 1, 1. But the CFL is 1 on the edges because we've got Newmans here, and 1 plus 2 dt because they're an internal point. So there's no mistake. B is the old temperature vector. Here, B is your external boundary conditions, the temperatures at your outer bounds. You should remember your selection of boundary conditions will influence the associated elements of A. So如果 you have a steady heat transfer and you want one boundary to be Newman boundary, which is fine, you need to change this to a 1 and remove the associated b term, make it 0. Then you'll get the right answer. You can't have 2 Newmans for steady. So that's why sometimes people use commercial software and they build their problem and they set all of the boundaries by accident to Newman, and then the software tells them that the matrix is singular and they don't know what it means. It's because they can't find a solution. That's why. Alright, that's the end of this part. So I've just derived how to build the A matrix for steady and unsteady. Now we're going to look at how to solve that stuff. How to solve the AX equals B system. Let's get started on that. Alright. Okay, let's get cracking. So I've just discussed using an implicit technique, using implicit solvers, we are going to create matrices AX equals B. So we need to build A and we need to build B and we need to solve for X somehow. The form of A and B depend on your boundary conditions and your steady or unsteady solution choice. You need to be careful here. It's easy to make a mistake with your A. 其实如果我等下会教你自己算这些 steady 还是 unsteady 的问题。If you have trouble, 大概都是因为你的 A 还有 B 有问题。Solving the AX equals B in MATLAB is easy. Solving in C is not so easy. You're going to discover. 我会先请你用 MATLAB solve and then move it to C. You want to check to make sure your A and B are correct. Regardless of what we're doing, 那个 A matrix for unsteady or steady 都是 positive, definite, symmetric, diagonal. So the type is basically the same. There are some minor differences. So yes, because the matrix is so nice, positive, definite, diagonal, are very neat and predictable, symmetric, we can use direct techniques to solve the problem. As we see later, there are many attractive options for this because A is so nicely sorted, but today I'm not going to talk about direct techniques. You might be familiar with some of those direct techniques. One of my favorite is using orthogonalization, Graham-Smith, QR. Yeah, it's a really nice technique. I'm not going to teach that to you today. I could. Instead, I'm going to show you CG and JACOBI. CG, you guys may have heard of, conjugate gradient. JACOBI, you already know, even if you don't know it. I've already taught it to you. I showed you last week. Anyway, let's go. Let's continue. So, these two methods, CG and JACOBI, may be a little bit troublesome from an implementation perspective, but once we move away from MATLAB and go on to C, it's going to be good because writing a solver to solve the matrix directly in C is not so much fun. MATLAB is easy, you just type I and V and that's it, you're done. But C, it's not so straightforward. There are libraries designed to assist you, so you can go online and download those linear algebra libraries, and then you can just find an inverse function and go crazy. But that won't be your work. It will be someone else's. Today, you'll be writing your own code from scratch. 你自己的 code 你要自己写 today, before you go home, before dinner. You're not allowed to eat until you're finished. That's a good reason to finish, right? We cannot rely upon MATLAB once we switch to C, which means we need to find a way to invert that system. Finding the inverse directly is a real pain in the neck, so we don't want to do that. All we need to do is find the solution to the AX equals B system without solving for A minus 1 directly. So that's our mission. There are lots of ways to do this. The easiest and worst way would be to use something like JACOBI or Gauss-Seidel or SOR, the single family of worst iterative solvers on the planet. They have terrible convergence properties, but they are really, really easy. You've already got codes for JACOBI in your computers if you were here last week. And I'll tell you why in a second. Both of these techniques are related. JACOBI and Gauss-Seidel are almost identical, but there are some catches. Gauss-Seidel should be done serially. What we find is JACOBI is easier to parallelize because its equation for solving for x, the iteration process, for every individual x inside this array is independent of the other x's. So it's what we call embarrassingly parallel. We'll look at JACOBI for this reason. JACOBI method. If you want to find the derivation of the JACOBI technique, where will you go? Well, you have lots of choices. 你现在在台大的数学系, right? You could go outside, you could ask Professor Wang, you could ask any of the professors outside. You go to Chengda and ask me. You guys are going to go to Wiki, right? That's what you do. Type Google and go to Wiki. There's a whole page on this. If you go to Wiki, there's a whole section on showing you what Jacobi means and where it comes from. I don't need to explain to you how Jacobi works because it's so easy. You'll find all the math and then the final equation is straightforward. Given this system, AX equals B, our A in this case is sparse, but it doesn't need to be. Jacobi assumes that you've got a diagonal, symmetric, and diagonally dominant matrix. This is the number one rule. So the diagonal terms have to be bigger than the off-diagonal terms. So if it's not, Jacobi won't work. Gauss-Seidel will, but Jacobi won't. Here is the algorithm. If you go to Wiki, go to Google, Wiki, Jacobi. I hope everyone's going to do this soon. Here is the equation that you get from Wiki. I stole it. I hope they don't sue me. It's that easy. Here is the flow chart. I did not steal this. I made this myself. That's mine. If you want to know exactly how it works, well, we're going to have nested for loop, right? Here's a for loop. Here's a for loop. Basically, this nested for loop is to compute this guy here. Then we look at the source term, subtract that sum from the source term and divide by AI. The technique is actually quite straightforward. Here's the algorithm. So if you want to have a look at how to do this, you can look at this. But what does this mean? Let's see. Here is our A matrix. Here is our X matrix. All we're going to do is for every X, for every temperature, we're going to take this times this plus this times this plus this times this. But, 如果 this is I, this is J. If I is equal to J, then we don't do it. So that means we don't take into account diagonal terms. We only find the sum of the non-diagonal terms. So in this case, we take this guy here. Let's say we're looking at T3. We take this guy times T2 plus this guy times T4. Add them together. Take it away from T and divide by the diagonal coefficient. That's it. Pretty straightforward. So for every row, we take the non-diagonal terms, sum them up after multiplying by T, subtract from the source term here, divide by the diagonal term, piece of cake. My flowchart, it's the best flowchart in the world because I wrote it. No one understands that. All right, copy this. What's it mean though? Actually, it's related very, very closely to FTCS and your finite differences. So let's have a look at our steady representation for the 1D heat transfer equation. We have, for steady flow, for steady heat flow, the time derivative is gone and we only have one of the right-hand terms plus one of the left-hand terms minus two of this one, right? We want to solve for that T of I. We want to solve for T of ij. Well, in this case, it's a 1D problem, so we're looking for Ti. All we need to do is move this guy over to the right-hand side and divide by 2. So we have T of ij equals a half of this plus this. Believe it or not, like magic, this is equal to this. This equation is equal to this when that's actually B of I, not B of II. I wanted to change that, but I forgot. This term, this is 0, this is our B. It's 0 for most inner points. So that's disappeared. 1 on AI for steady heat transfer, that's 2, right? So there's 2. And AI plus 1 for steady heat transfer is -1. A of I minus 1 is -1. So the equation is identical. So you take your finite differences using FTCS, but FTCS doesn't mean anything because it's steady. So just central differences. And you solve for T of K plus 1. You'll find that the temperature of K plus 1 can be computed in terms of the other temperatures, just like that. These two equations are the same. So it's no surprise that Jacobi works, because the computation can be related back to your finite difference representation. So it's very physical. So they mean the same thing. Now what does that mean? It means that the convergent qualities of Jacobi, namely the convergence rate, the rate at which the system solves, and the nature of the evolution, how the solution T changes with iteration, is basically exactly the same as your FTCS algorithm. So if you use a Jacobi solver to solve this problem, if you use Jacobi to solve this problem, here's your initial condition, which doesn't mean anything for steady, but it doesn't matter, because for Jacobi, you need to start with some estimate of t to progress the solution. So here we are. You see that the next solution k is based on the old solution at the next solution iteration k plus 1 is based on x at k. So to start JACOBI, you need to have an initial condition, I guess. Let's say you set the initial condition to this. After some iterations, the solution is going to look like this. Does that look like your unsteady solution? One of your unsteady solutions after a certain number of time steps, right? Each end last week, the FTCS 120 Young. Because it's the same maths. The equations are the same. The procedure's the same. So as you progress with JACOBI iterations, the solution solves just like an explicit solver. You see the gradient form, and eventually it will level out and you'll get your steady solution at 0.5. So you guys can check this yourself. You can write your JACOBI solver using this equation here. Yep, that thing there. And you'll see that the evolution of t, or evolution of x, as you iterate, looks just like FTCS, the unsteady solution. So why do we do it? I mean, the convergent properties are the same. The only reason that we use JACOBI is that it's easily parallelized. But guess what? FTCS is also easily parallelized. So there's not much of a reason to do it. One may draw a similarity between the iterations required by JACOBI for convergence and the number of time steps required to reach a steady state solution using FTCS. So the number of iterations required by JACOBI to converge on the solution is almost the same as the number of time steps you require using FTCS to reach a solution. Isn't that interesting? If you had to ask me, what method would I use, JACOBI or explicit FTCS, I would recommend using explicit FTCS every time. You can, using Gauss-Seidel, using SOR, you can over-relax. Have you guys heard of this term? You can force the relaxation coefficient to be a little bit larger, which means we multiply one of these by some value to accelerate the convergence. That just means you're increasing the time step, right? For FTCS, it's like the same thing. You're increasing the CFL. Likewise, you may have heard that over-relaxation can cause divergence when you're solving, because the stability criteria for JACOBI is very similar to the stability requirement for FTCS. Maybe not so stringent, but it's still very, very similar. So today, I'm going to ask you to solve a steady problem. You can use JACOBI, but the code is going to look very much like an unsteady FTCS solver. It's your call. Conjugate gradient is a completely awesome technique. Now, the mathematics behind the conjugate gradient method will kill everyone in this room, so I'm not going to talk to you about that either. The trick is, why are we going to resort to a Krylov subspace technique? Krylov subspace is a completely, in fact, if you're familiar with vector projections and rotations and all of Given's and Householder's stuff, I'm a big fan of that stuff. If you are, then you should read up on conjugate gradient and the generalized minimal residual technique, GMRes. That's also a fantastic solver. They're very fascinating. The motivation for us to learn something like this, because I'm an engineer, right? I really don't care. I didn't care much about Krylov subspace. I just want the answer. I just want to build my plane and fly it. That's what engineers do. What we need is a system that can solve AX equals B faster than explicit FTS, faster than SOR, faster than Gauss-Seidel, faster than JACOBI. We need something which converges faster than the techniques that we already know. Explicit FTCS is very easy to code, so that will work every time, but you have to limit your CFL. We want something faster than that. JACOBI is not faster than that, because it's basically the same thing. Gauss-Seidel, not much better. But CG, the convergence properties of CG are completely unrelated to the physical process of heat transfer. That's why we use it. We're guaranteed to converge faster than FTCS. The CG technique, you may have heard of this. CG method was originally conceived as a direct solver, and with infinite precision, if your computer is infinitely precise, then it is a direct solver. But your computer is not infinitely precise. On any real computer system, we have floating point errors. So as you perform CG iterations, floating point, rounding off errors cause you to go further away from the solution, which means you often need to take more steps than theoretically required. So we envisage CG as an iterative solver. we require a large number of steps to solve this AX equals B system, but the number of steps is much, much, much lower than JACOBI, Gauss-Seidel, SOR, over relaxed SOR. Now, before we continue, we need to introduce something called the residual to you guys. So if we have an AX equals B system, if this x here, our solution of x, is not the correct value, is not the steady value or the correct value at any given time, we will find that AX does not equal B. 所以如果我们是让选 x， 如果我们让选 t， 我们会发现 AX equals not equal to B. Let's see, if this is all zeros and B is non-zero, 当然 AX is not equal to B. So we need to find a way to measure how bad our estimate is. How far off are we? And the easiest way is to look at the residual. Residual is what's left over when we substitute our guess x in. So we have AX equals B, so B minus AX is going to be a vector of errors, right? Something like an error. We can use that residual R to tell us how far away we are from the correct answer. If R equals to 0, that means that B does equal to AX, and we win, we're finished. So our mission is to make that residual 0. Now the problem is that that residual is a vector. It's a large vector. So we have B is a vector, A is a matrix, X is a vector, matrix vector equals a vector. So we have AX equals a vector, B minus AX, that's also a vector. If we have 100 elements in our 1D problem, then we're going to have 100 residuals. How do we measure the error then? Well, we actually need to take the dot product of that array. So the total error, we're going to claim is going to be something like RTR. So we take that vector of residuals, transpose it, multiply it by itself. So that's a dot product, right? You guys know dot products? Math department, heaven help us if we don't know dot products. R dot R. We're going to multiply everything by itself, so it's going to be the sum of R squared. You guys might be familiar with that term too. Yeah, that's important because when we do parallel computing, that's not going to be easy to compute perfectly in parallel. So that's a sum of residuals squared. That's often how close, that's how we measure how close we are to a solution. That's not just used here, that's used in many areas of math, like least squares solutions. In fact, CG is a solution to least squares problem. Alright, so we need that RTR, we need the residual squared, sum of residual squares, to use CG. The remainder of the computations that we use in CG are either matrix vector computations or dot product, just like RTR. So the good news is, why is that important? A matrix vector calculation. That's quite easy to program in C, right? Yes, Professor Smith, I can do that. I'm going to do it today. Alright. Dot product computation is also quite easy to write in C. So because this is easy and this is easy, writing CG in C should be still pretty hard actually. But we're going to try to keep it easy. So we'll see what we can do. Each of these computations is relatively easy to program in MATLAB and or C. 我会建议先用 MATLAB. I'll tell you why in a second. After you've got your MATLAB code working, swap to C. One potential problem, however, is this dot product thing. For today, it's not going to be a big deal. 应该不会发生什么问题，因为你们今天不会写那个 parallel computing. But when we do parallel computing, once we start doing parallel computing, this dot product is not a fun thing to handle because it is impossible to parallelize it perfectly. Bad luck. But the other one's fine. So, how do we use CG? Well, just like JACOBI, we need to start with an initial guess. The initial guess might be something you think is close to the solution. That's nice. If you can do that, that means you're going to converge quite quickly. If you want to be silly, you could set an equation like this, or you could set everything to be 0. That's fine too. That's what we're going to do today. So we're going to assume that we have no information about a good initial guess. We're just going to set our initial x vector, our initial temperature vector, to be 0 everywhere. So we're just going to say the whole thing is frozen. So we're going to use x equals 0 because we don't have any magical insight that provides us to a general solution at this stage. 如果我们有的话, then we can use it. So if we're going to use CG to solve an unsteady problem, which we can do, then we can use the temperature at the previous time step as our initial guess. You might think this is quite an obvious thing to do, but last year I went to a mathematics conference and I put my hand up, and one of the presenters was doing unsteady heat transfer, and he was setting the temperature to be 0 at every dt instead of using the previous dt as a starting estimate for x. I think I saved his program like 99% of the computational time by changing one line in his code. Anyway, let's have a look. CG method also requires a direction vector p that helps control the convergence. So a direction vector p tells us which way we're moving when we're converging to the solution. I can tell you right now, 如果我开始说我们的 x 是0, now our p vector is going to be equal to b. Also, if x is equal to 0, our residual is b minus ax, right? If our residual is b minus ax and x is 0, then our residual is b. So 开始的时候我们开始用 CG, 我们要先选 x 都是0, 我们今天说0. 我们还要选 p, 我跟你说如果 x 是0, 那 p 是 b. And if x is 0, now r is also equal to b. 所以我们准备好我们有 x, p, r, 那我们可以开始算 CG. How do we do it? Well, CG is an iterative procedure. We need to take many steps. We're going to continue to iterate until our RTR is small or our maximum number of iterations has been reached. 今天你 test your code 的时候，如果你使用 more than 100 iterations, kill it. Not with a gun, just turn it off. Tell it to stop iterating. 100 iterations for a 100 test problem should be sufficient. Alright, let's go. So, once 我们已经选好了 P, X, R. Next step, compute AP. That's a matrix vector computation. So that provides a vector. Step 3, we take AP and we calculate P transpose AP. AP is a vector. P transpose is a transpose of a vector. So that's a scalar quantity. We need to store that. So let's see. AP, PT, AP, that's a dot product of P and AP. This is a matrix vector calculation, step 2, so that's good for parallel computing. This is bad. Step 4, after we've got PT, AP, I also want to compute our RTR, the sum of residuals squared. That's a dot product of R and R. That's bad, that's a scalar too, that's fine. Keep going. Step 5, alpha. Alpha is a radius, the ratio of your sum of residuals squared divided by PT, AP. That's a scalar computation as well. So that's just actually a simple number crunching exercise. Step 6, we're going to use alpha to update x by saying that x equals the new x, the solution of our problem, is equal to the previous guess of x plus alpha times your p vector. So x equals x plus alpha p. That gives us our new estimate for x. After that, we need a new estimate for our residual. Actually, many ways to do this. I'm calling the new residual r star. If you wanted, you could compute the new residual r star by going b minus ax star, where x star is your new temperature, computed in step 6. There is a better way. 我等下来跟你说那个是什么。Beta is the ratio of your new residual to your old residual, and that allows us to update our direction vector p, where p is equal to your new residual plus beta times your previous direction vector. That's CG. What are you guys going to do when I tell you to start using CG? You guys are going to go www.google.com.tw and you're going to type in CG wiki, right? You won't regret it, I promise. Let's have a look at the flowchart quickly. So we set our x vector all to be zeros. We set our p vector to be equal to b and r equal to b. Then we pick some, we say we iterate until RTR is less than some value. Don't be too small. I promise you, if you pick some really small value, then your computer will blow up. I'll explain to you why. I predict that at least one person here will blow up CG today. I'll be looking for it. Okay, we first calculate AP, then PTAP, RTR, alpha. X equals, here we are. We make an approximation here. Instead of computing x, x equals x plus AP, here I calculate R star equals AX minus B. There is actually a better, more efficient way of computing R star. I'll tell you what that is in the next slide. Then RTR, our new residual sum of residuals squared. Calculate beta, the ratio of R star T, R star divided by RTR. And update P with beta. And we just keep going until RTR is small. The way that we speed up this algorithm, we replace, see, R equals B minus AX. That's actually matrix vector computation and a vector addition. That's actually quite computationally intensive. We can replace it. We can say that R star is equal to the previous R minus alpha AP. That will give us an estimate, a new estimate for R star. This is less computationally expensive. It does have a lower parallel efficiency, but not by much. The key is that this approximation assumes infinite precision. If you compute the new residual matrix by saying B minus AX, then you're going to compute the correct one. But if you keep saying R star is equal to the previous R minus alpha AP, your errors in rounding point, your rounding off error will accumulate and get larger and larger. So your R star could potentially get worse and worse. So you could be moving away from converging. But if you're using double point precision, that's not going to happen today. You guys will be fine. For today's problem, this may introduce rounding errors. If you're doing a PhD in this stuff, be careful of this. If you guys are just here to have some fun and do some heat transfer, we'll be fine. Okay, let's set up a CG solver in MATLAB. Hang on. We don't have a MATLAB code yet, do we? But here for your reference is a matrix A. I'll put this up later, and B. So we have some random matrix A. It's not so random, let me tell you. And some vector P, 1, 2, 3, 4. We want to solve this system of equations. We need a MATLAB code. What are you going to do? www.google.com.tw, go to Wiki. On Wiki, there's a MATLAB code for CG. Hooray. You're going to steal that. You don't need to write your own. In fact, there is a CG code in MATLAB all ready to go. But because you need to write a C version, you may as well write properly your own MATLAB version. Here it is, each of the steps. AP equals A times P, alpha. RS old, the old residual divided by P transpose times AP. It's all there. And they even cheat and use the R equals R minus alpha times AP. So they don't use the correct way. They use the dodgy way. It's not that dodgy, but it's not exact. And then they say if your residual is less than some value, kill it. Otherwise, update your gear. P is, you update your P vector and reset your R. So all you need to do is kill this, copy it. So you should have no trouble using Control C and Control V unless you've got a Mac. Because Control C is not going to copy in a Mac. You'll figure it out. Yeah, save this code to your own MATLAB. You're going to use it. So if you want to solve it, you just type CG method. I saved my file as cgmethod.m. Put in my A and B. There's a solution. Here is the residuals. If you want to check this is correct, you can substitute them in. If your condition number is high, and you might discover this today. For example, if your CFL number is very large, you're going to get a high condition number. If you have a high condition number, you may need to use preconditioning. Guess what? Today you don't need to. I promise you. 我们今天不用担心那个 preconditioning 的东西，我只是要跟你建议一下，如果有一天你要算一个类似的问题，你发现了那个 condition number 太大了，你要改一下那个 CG 的 method. So here, guess where this is from? I'll give you one guess. I stole it from the internet. What web page did I get this picture from? Wiki, people. What am I? I took this from Wiki. Basically, if you're using preconditioning, what you really need is the inverse of your preconditioning matrix. This is quite familiar to you guys, and we modify our algorithm accordingly to take into account our preconditioning. So if your condition number is very high, you'll need preconditioning. Otherwise, you won't. Let's go. All right. 时间到了. It's time. If you haven't turned on MATLAB, you better turn it on now, because we're going to work together through MATLAB. And then I'm going to give you your nightmare problem, which you need to compute before dinner. Yeah.
10 minutes break or something?
Yeah, that's fine. Yeah. 你要跟他们讲吗? Oh, guys, before we start with the actual work, 到现在你只有听我的讲话而已. We're going to start working now. 我会建议先去喝水，去尿尿. Go get a snack if you need one. I'm going to take a break myself. We'll be back in 10 minutes. We'll get to it. 现在几点? What's the time? 3 o'clock?
It's 3.
Yeah, wonderful.
3 o'clock.
Everyone here should be able to finish, hopefully, the challenge problem before 4:30. Good luck. But let's talk about how we're going to get started first. So we have to remember we've just covered 2 techniques. We've covered how we're going to solve an implicit unsteady problem and an implicit steady problem. So 2 different kinds of solution techniques. They're both implicit. One is time accurate, the other one is not. The other one just gives you the steady solution. The mission is the same. the goal is actually quite easy. First, doesn't matter if it's unsteady or steady, you need to build an A matrix. Your A matrix will be different if it's steady or unsteady. Then you need to build a B matrix. Again, your B matrix will depend on your steady or unsteady solution. If it's an unsteady problem, your B is just your initial temperature. If it's a steady problem, then your B will be your boundary condition temperatures. That's about it. So building B should be the easiest part. That will be the hardest part. Once you've got A and B, then you need to solve this problem. In MATLAB, we're going to use MATLAB first. We solve this system by using inverse of A. Once we start using C, a little later on, we can't do this. We need to use JACOBI or CG to solve this system. Alright, so have a look at our A matrix for the unsteady problem. We can see that we're going to have the same diagonal terms, 1 plus the CFL number, a single CFL number if we're using a Newman boundary condition, or 2 of these CFLs if we're not, and we have negative CFLs either side. So this allows us to formulate the explicit solution as an implicit solution, and we're solving the AX equals B system. MATLAB. So thank goodness we're going to continue to use MATLAB to basically test our problems out. If we're going to write a single MATLAB code, a simple MATLAB code, well, let's see. Our mission is to build A and B. Right, that's the first mission. If we want to make A and B, then we need to set the CFLs, right? So let's see. So this is a MATLAB code for an unsteady implicit solver. So we're going to show you how to build your A matrix. So I'm going to zoom in on that guy. I don't have my mouse plugged in. I need that. Oh, it's not going to let me do it. Hang on, give me a second. There we are. All right. So let's have a look at this code. This is a simple MATLAB code. You can call it whatever you like. It's going to be the 1D problem again. We're going to use 1D to solve this problem. Or we'll solve a basic 1D problem. The same 1D bar problem we looked at last week. It's going to be a 1D bar. We're going to have 100 cells. So we're going to go from 1 to 2 all the way up to 99 and 100. The length is going to be 1. We're going to use Newman conditions on the left and right ends. And our initial temperature is going to be a step. So the same 1D problem we looked at last week. We know the solution. You guys have all got your own FTCS codes. So we know what this should look like. So we're going to use the same constants. We're going to set n equals 100, 100 discrete points. We're going to set our initial temperature to be zeros everywhere. We'll change this in a little bit. L equals 1. dx is a spacing between your points. That's L on n. Our dt is the same. Ling dian O by 10 to the negative 4. Chisha, you guys should be able to cut and paste your code from last week if you were here, and use that. We only need to cut and paste the front part. I introduced a new variable z equals theta times dt divided by dx squared. That's a CFL number. We only need to compute this once because it doesn't change. Now we need to start computing our A matrix. Now our A matrix, you might have recalled, I'm going to use Newman on the left and right hand sides. That means our diagonal terms for the first and the last elements in our array are going to be 1 plus a single z, 1 plus a single CFL. We can go back to our page here. You can see this term here is 1 plus z, 1 plus a single CFL number. So in our code here, if I equals 1, we're on the left hand side. If I equals n, we're on the right hand side. 我们的 A 我们的 diagonal term, 所以我们写 AII 就是 A11 or ANN. That's going to be 1 plus z. 如果我们不是在最左边还是右边，我们在中间， That's an else. 我们的 AII 就是我们的 diagonal term must be 1 plus 2 of those CFLs. See, 1 plus 2 CFL. Piece of cake. So here, in this line, from line 16 to line 20, we are building our diagonal terms of A. 当然我们还要 set A. Oh, Matt, you know the good thing about MATLAB? 如果你以前没有跟 MATLAB 说那个 A 是什么，它会 build zeros for you. So good thing for MATLAB. Otherwise, we need to initialize a matrix of zeros. So we've got our A's on the diagonals. 我们看右边, the right-hand term. So that means we're on any point. And if our right point here is a real point, that means we need to modify our A matrix. We have a look. A of ith because we're looking at the ith element. And we're going to say I plus 1 because we're looking at the element to the right of the diagonal. That's going to be negative z. Likewise, if you're larger than 1, which means you're away from the left boundary, that means you have a real cell to your left. So we look on the term left of the diagonal and make it negative z. Gongxi, you've built your A matrix. Can you believe it? That's it. Please, everyone, if you haven't already started, use MATLAB to copy this code right now. And that is a short explanation of what that all means. This is the A matrix that you're building. 当然你的 A 是多少？应该是100乘100吧。Your A matrix is 100 by 100 matrix. I haven't written 100 by 100 here. I've only written the first and some middle points and the last. But when you look at your A matrix, you should be able to see that it basically looks like this. Well, a little bit of an explanation again. 如果 I equals to 1 or I equals to n, 那我们就是在那个最左边还是最右边 of our 1D bar. So we have to set the 最左边的还有最右边的 parts to be 1 plus z. 1 plus z. 如果我们在中间, then we don't have to worry about the Newman boundary. They're all 1 plus 2 z's, all along the diagonals here. So this red term here corresponds to the left-hand side and the right-hand side of our boundary problem. These are the inner terms. So the first part of this code here should give you the diagonals. Should correctly compute all of the diagonals. The other two terms, this is the left-hand neighbor, the right-hand neighbor and the left-hand neighbor. So the red term here is in the cell to the right of your term, of the current one you're computing, and the light blue here is the one to the left. So we can see here, this guy corresponds to this guy if we're looking at this row, and this one is the right-hand side. So basically, red and blue are your off-diagonal terms. That's what we're computing. So please use MATLAB to write this code now. When you're finished, I want you to write this for me. I want you to take, after you finish, run it, save your results using save results, save it to file, then type SPYA. And show me what you get, please, once you're done. SPY is going to let us have a look at your matrix to see if it's the correct form. You're familiar with SPY?
I think the guys have taken the mathematical software, that kind of thing. Or
Yep. Let's see how they go.
But the computational mathematics, they should be familiar with the SPY.
What? And you should be able to see something like this. Once you type SPY of A, it's going to present a graph for you that's going to show you all of the internal points. You should be able to see a diagonal set and a set of off-diagonal terms. Each element of A is going to have 3 parts, the diagonal and 2 offsets. So that's what SPY should look like. More precisely, because SPY doesn't tell you what the magnitude of each element is, it just tells you there's something non-zero there. So if you really want to see if you're right, then you need to check the condition number of that matrix. The condition number should be 1.998. If it's not 1.998, then there's a mistake and you better show me quickly. And that's it. So we've built A. Gongxi, we're almost there. All we need to do now is build B. Now this code is an unsteady implicit solver. So B is going to be an array of our initial temperatures, which we already have here. So we already, conveniently enough, we've created an array T that holds our initial condition, which is the same as last week. That's our step problem. 所以如果你目前还没有写这个 t 进去 you want to put it in now because we're going to use it now. Your condition number should be 1.998. I think everyone's there now. What is interesting is, and you should have discovered it, I already told you once before, as we increase dt, the condition number increases. So it's easy for us to solve this system when we have a very small dt, but as we increase our time step, the condition number increases and we see that the problem gets harder to solve. Unfortunately, it's not really linear. Should go actually with dt squared. That's what you should see, I believe. So if you can try for yourself, right now your CFL is linjer O because your dt is 0.25 by 10 to the negative 4. If you change your dt to be 1 by 10 to the negative 4, that means your CFL is 1. If you type condition, you should see that your condition number has jumped up to 5. If you go to CFL 5, then you should see your condition number jumps up again to 21, about 21. So this is a bad thing, right? Because as your condition number gets larger, your matrix gets harder to solve. Now these condition numbers are not big yet. These are quite low, so we're not in any trouble. But if your CFL was 1 million, which is possible for an unsteady solver like this, that means your condition number is going to be very, very, very large. And we're going to visit this situation a little bit later on. Now, back to the code. We've got B, 我们的 B 就是 T. We have our old T. We have our A. 我们进入备好. You're ready for the magical formula now. It's not rocket science. Well, I guess it is if you're using this code to make a rocket. We only need to add a small piece to our code, and you're going to see it's an unsteady solver, so we have to iterate over time. So we're going to have a for loop for I equals 1 to number of steps. So we need to iterate over a certain number of time steps. You can choose. All we need to do is type t equals, well, let's see, we need the inverse of a. So first we're going to create a variable called a, I, and v. That's going to be the inverse of your A matrix. Since your condition number is finite, you have no trouble computing this inverse, and we're just going to type t equals a underscore I and v times by t. And that's it. You're finished. That's your unsteady flow solver. Nice work. It's much, much easier than FTCS. This part, at least. All of the real work went into making that A matrix. If you make a mistake in this method, it's often not because you make a mistake here. You can't make a mistake here. It's too easy. Most people make a mistake in their construction of A. So please go ahead and modify your code. Run for me 1 or 2 or 3 or however many time steps and show me your answer. Please update your MATLAB code now. Now, the code as it's written here, you'll see that the number of steps equals 1. 所以这个会跑一个 dt 现在. But you can change it to run as many dt as you like. We already know what the solution should look like, so you should have an idea of where the answer is going to go. But once you finish writing this, show me your answer and we'll see how you went. Received, what you should have all computed was, if your code is right, if it's not right, I'll find you. I'll get you. If you set your dt to be 0.25 by 10 to the negative 4, and you run your solution one time step, your solution should look like this. So I'm pretty sure I checked most of the people around here. Everyone's code should more or less give you this result after one time step. Last week, we also looked at the same thing. We did explicit FTCS. We set the dt to be 0.25 by 10 to the negative 4, and we ran a single step. And the result looked a little bit like this, but was it exactly the same? No. Because for explicit FTCS, we were only able to adjust the values of this point and this point after a single dt. But in this case, we're using an explicit solution. It works differently. Let's compare the results. So on the left-hand side was last week's answer. Explicit FTCS. Using the same dt, 0.25 by 10 to the negative 4. That's the result from last week. That's this week. The right-hand side is this week. That's implicit. Same dt. But the solution's different. And the reason is because with our implicit solver, we can compute all of the dt's at the same time, so we're able to get a better answer. In the FTCS, we can only update the value at any 2 points. I'm going to need my duster again. Based on the condition of the temperatures around them. So let's have a look at the reason why. Here's our initial condition. So we have 1, 1, 1, and t equals 0 here. Using FTCS, when you compute the new temperature for here, the new temperature here is the old temperature minus the CFL times by this plus this minus 2 of this. So it will change, right? It will change. This cell here, the new temperature is this minus the CFL times this plus this minus 2 of these. 1 plus 1 minus 2 is 0. So it's a guy. He hasn't changed. So this guy here, using FTCS, cannot change after a one-time step. But guess what? Implicit, this point here did change. Because it can, because we compute all of the new temperatures at the same time. So we can allow heat to move further in one time step than otherwise might be possible. And that's a pretty neat thing. Now, you might be thinking this is a good thing. It is not a good thing. Sometimes this is called dispersion error. Implicit techniques have an associated dispersion error with them. Now, I'll be presenting a talk on dispersion error next week at a finite element conference. If you're interested in going along, the actual analytical solution should be somewhere between this one and this one, in the middle. Probably closer to this solution than this one. If you want to know what the analytical solution is after a certain time, do you guys know how we might be able to solve these equations? Fourier series. Take a Fourier series. Use Fourier series to find the analytical solution to the temperature at all of the points. Evolve them one time step and you should be able to find out what the actual analytical solution is to the heat flow at any given time. That's one tool. I'm not going to go over that today, but if you're interested, I can tell you how to do it. You should find that the actually correct solution is closer to this, but somewhere in between. Neither one is right. Of course, they're both numerical approximations, but this one's closer. So we see that in a single dt, the implicit solver will actually adjust many cells. This cell might be 1, but all of the cells close to that initial interface, they are not 1 anymore. They've been adjusted. Same with these guys down here. Using FTCS in a single dt, only this cell and this cell will have their temperatures changed. So if you have a disturbance in your flow field and you use explicit FTCS, that disturbance can only propagate one cell every time step. But using an implicit technique, it can more or less propagate at the correct speed, plus or minus your dispersion error, which we're not going to talk about here. So the solution's different. What we also found last week was that the FTCS method had very strict stability requirements. 如果你的 dt 太大了，我们开始说 dt 是 1 by 10 to negative 4. If your dt was that large, 那你以前写的 FTCS code will break. You'll get the wrong answer. Your implicit code, you should have discovered, 如果我有给你看, that's alright, 应该也有自己发现, if you play around, there is no such stability requirement for the implicit approach. You can make dt anything, and you can still compute the solution. But as your dt gets larger, your dispersion error is going to get larger, but you guys can't see that. We don't want to talk too much about that. Since we can compute the new temperature all at the same time, we can make dt as large as we like. So let's have a look at what will happen. If we set dt to be 1 by 10 to the negative 4, 如果你使用 FTCS, this is last week's unstable answer. You see these wiggles appear, local minima and maxima in your solution. That means that your solution is unstable. If you use implicit to set your dt to be 1 by 10 to the negative 4, you'll see this stable result. So it won't crash. You can actually set your dt to be as large as you like and attempt to compute the correct solution at that time. However, you have to be wary of dispersion errors. So what I did, just for fun, I set my dt to be equal to 1. Not 1 by 10 to negative 4, not 0.25 by 10 to negative 4. I set my dt to 1. That's like taking 10,000 time steps of 1 by 10 to the negative 4, right? So I take 1 dt, 1 time step with dt equal to 1, and this is my solution using implicit. Here's my solution, my explicit solution after 10,000 time steps. This is my solution after 1 implicit time step with dt equal to 1. You can see they're more or less, they coincide approximately. We do pay a price. The condition number, if you type condition number A, has jumped up to 40,000. Actually, that's not too bad. That condition number is not too large. But if you really want to go super steady, your dt should be something like 10,000. Then your condition number jumps up to 100 million. It still works, but with a condition number of 100 million, you're starting to get into the danger zone of condition numbers. You're starting to approach singular. Because remember, our steady problem has 2 Newman conditions on the left and right hand side. The more you take a dt out of that equation, the more you increase dt, the closer to singularity you're getting. The higher your condition number will be. Soon you're going to have a matrix which is nearly singular, and MATLAB will tell you your matrix is nearly singular. You're in big trouble. 它根本不会跟你说 you're in big trouble. It just says you're nearly singular. Alright, so what did we just do? I just gave you a MATLAB code, a very simple MATLAB code that solved for the temperature at any time using a transient problem by computing A and solving for the temperature at any time. The challenge problem today, I'm going to show you quickly, and then I'm going to show you the code that I wrote for JACOBI. 我要给你看那个 JACOBI code just so you know how to make it work. The challenge problem today is going to be a 2D problem. 其实如果你的问题是 2D, 3D 还是 1D, 应该是跟你的算法没有什么关系. After you compute A, 我们的工作是一样，我们只要算那个 AX equals B 的结果. So it doesn't matter if it's 1D or 2D, your work is still the same. 如果是 2D 的话, you just need to change how you compute A. So you need to figure this bit out. It's not that tough. I'll explain a little bit how in a second. The other challenge is you need to write a solver in C++. So you're either going to have to do a JACOBI solver or a CG solver, or 会建议 CG. You need to, so that's the first job. Make your code run in C++. So for your 1D code that you've got running now in MATLAB, 我会建议 write that 1D code in C. Then in C, write your CG or JACOBI solver. Make sure that your C code is the same as your MATLAB code for 1D. Then change your code from 1D to 2D. 你应该只要改你的 A 还有 B 的计算而已. That's all you need to change. And then your CG 还是 JACOBI solver 它都是一样，因为它不知道那个 A 还有 B 是怎么样. Alright, two-dimensional discretization, let's do it. This is what we did last week. This was your two-dimensional problem from last week. If you want, you can use your 2D code to solve this week's problem in case you need the answer. I will tell you the answer, so you don't need to worry too much about that. This is what we had to work on last time, a two-dimensional square domain. We needed to compute the steady temperature distribution. Here are the equations we used. So we did explicit transient FTCS last week. So we had an FTCS discretization with a time derivative on the left, and we had all of our spatial discretizations in the middle here. That's a y, dy squared by it. But I did fix it up down here. 如果我们的结果是 steady 的话, then we can get rid of this time gradient and we have these two here. Those two equations here. So your first time derivative is gone and we have these guys here. That means you're solving for this system. We're trying to solve for Tij. 你看我这里有写 k equals k plus 1 equals k minus 1, 因为我们没有一个 time. 它们都是一样的 time. That's the most important thing. So we've removed time from the equation now, and we're just solving for all of the t's at I minus 1, I plus 1, ij, etc., etc. All of those combinations of i's and j's. All of these temperatures are at the same time level. We need to solve them all at the same time. How do we do this? Well, let's see. We need to do the same trick we did for 1D. Rearrange to obtain the coefficients for each one. So we have theta on dx squared for t I minus 1 and I plus 1, theta on dy squared for j minus 1, j plus 1, and we have theta tij for these guys, and we have two of these on the right hand side. So our coefficients are going to be theta times 2, blah, 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 blah. Let's have a look at the actual equations. Here they are. So we can write them all into a linear system. So we have ti minus 1j, ti plus 1j, tij minus 1, tij plus 1. These are all the same thing, right? dt is not there, right? dt is dead. The dt is gone because it's a steady system. We're not looking at the transient system here. So we just have coefficients of theta on dx. You're going to find that those are going to disappear too. But, oh, by the way, that's dy squared. My bad. Oh, I haven't taken t out there. That t is dead too. That's 1. My bad. If you arrange this into a matrix form, you're going to see that's not there. Those are 1s. You're going to have minus 2a minus 2b on the diagonals, ab on the left and right hand terms. You're going to have your left up, center down, right, in some way written here. So again, actually there's a mistake in that equation there. You should be able to figure out how your A matrix is built. Oh, I've written a C code here. This is C. This C code works or computes for you that matrix. So in this instance, this A matrix is a correct A matrix for this problem. So if you want, you can cut and paste, or you can't cut and paste because it's a picture, but you can copy my code to generate in C that A matrix, 我会建议先用 MATLAB to create your A for the 2D problem. Then you can compute the solution quickly and easily. For your challenge problem, you can't use this idea. Let me explain why. So we have our init here. You guys may not or may not be able to see it. We need to iterate over all of the cells in our problem. It's a 2D problem, so we need to work out what the x and y cell are. We compute the diagonal term as 2 times phi x plus 2 times phi y. Phi x is going to be theta divided by dx squared. Phi y is theta divided by dy squared. Then we need to work out our boundary conditions. Those are here, and here. 如果我们是在一个 Newman boundary, then the coordinate corresponding to our other point is, well, basically we just need to set the neighbor because we have Dirichlet conditions, sorry, but we set all of the b's to be 0. We have a fixed temperature on the bottom, again, so we need to set b not to be equal to 0 there. Plus we need to set our initial guess, which is all 0. That was a solution to last week's problem. You guys should have no trouble with this. If you're using CG, you should be able to get the solution after 33 iterations for this many cells at least. I think this was 20 by 20, a 20 by 20 grid. So we had, let's see, the 20 by 20, that's 400 unknown, so our matrix is 400 by 400. And we converged using CG with 33 iterations, which is a lot faster than theoretically expected. That's a win, because it's a 400 by 400 problem. That's a solution. This is today's problem. This is what you're going to do today. Good luck. We do not have a square domain. You did the square domain last week. What we have is a rectangular domain with holes. 请你不要算 the temperature in this hole here or here. Those are not to be computed. What we have is a fixed temperature on the left-hand side, a fixed temperature on the right-hand side. All of these green surfaces are Newman boundaries. No heat flux allowed, which means the temperature on the other side, on the ghost cell, is going to be equal to the inner cell for all of the points along those green edges. I want you to compute this solution for me. I can show you the solution. That's a solution there. Your solution is going to look something like this. So your first job, 如果要的话，你可以用 last week's 2D FTCS code. Modify your FTCS code to simulate this if you want to, just for fun. Or you can try now, which is what I recommend, to create the A matrix and the B matrix for this monster, and then use inverse of A times B to get your steady solution. That's what you should be trying to do. It didn't take me too long to get the answer. Professor Wang will tell you, I wrote the MATLAB code to solve this problem on the Gautier today. I started writing the MATLAB code at Taichung after I looked at the Lantern Festival. So I was looking at the Lantern Festival and I thought, oh, let's solve this problem on the Gautier now. I started writing the code then, and I had the solution finished before Banchao. So you should be able to finish it before dinner. I think you can do it. If you get really stuck, you have the solution, right? Professor Wang will give you the code to compute the A and B matrix for E by 1 quotient. He wants to buy a Ferrari. You can't buy a Ferrari you can't drive a Ferrari very fast anyway. If these are the computation times in MATLAB, you can see 640 unknowns, that's the total problem size, that's the total number of cells. Took 0.04 seconds to solve in MATLAB, that's like that, right? The problem is once you go up to a very large number of unknowns, once we hit 10,000 unknowns, that's like 100 by 100 cells. By Tawny, do not use 100 by 100 cells straight away, because it takes a while. This one took 140 seconds to solve in MATLAB. Using CG, you get 33 seconds. The problem is if you use MATLAB's inverse A times T, it will use a direct method to compute the inverse. That's expensive. If you compute using CG, it's going to be faster. Using MATLAB's built-in software. If you use 16,000 unknowns, that's a lot of cells. That's 89 seconds using CG. MATLAB will not be able to do it analytically using INVA with this many unknowns. It will say it runs out of memory. Because with this many unknowns, you're going to create a matrix, an inverse, 16,000 times 16,000 large. And MATLAB won't cope, especially on these computers. Not that these are good computers, but they just don't have enough memory for that. So that's the kind of time you're looking for. Go for something small. On the Gautier, I did 30 by 10 cells. And that's not too bad. And the Jiggle Tabudo, it's not that bad. For your own reference, this is for fun. The computational times for different parallel architectures for very, very large numbers of cells. This is all C code, by the way. Using one core was 2,000 seconds. The fastest OpenMP core I got was 46 seconds. I showed you this last week. But this time, I put the GPU result in. The fastest GPU code I wrote was 11.5 seconds. So this computer, this OpenMP result, that was on 16 Intel cores. That's a dual Xeon system. It cost 300,000 NT. That's an expensive computer. This GPU cost me 36,000 NT. Much, much cheaper. And it's about 4 times faster than that server. So for this problem, GPU eats it up. This was using CG. So CG can actually run pretty fast on GPU if you're interested in learning about GPU. In the next class, when I show you guys, I will discuss with you OpenMP. I'll show you how to code OpenMP in GPU, and we'll do that in this room. That's next time. But your job today is this. So here's your initial condition. You need to build this A matrix first, build your B, then inverse A times B, and you're done. That's basically all you have to do. Good luck. I'm going to start helping you guys now. Oh, Paise, there's one more thing I want to show you. JACOBI, or Wangji Fengjin Chu, that PowerPoint. If you want to write a JACOBI solver, I'm going to show you the MATLAB code for JACOBI right now. Oh, I knew I forgot one thing. JACOBI. There we are. Oh, today, please. Oh, it's not going to work because I'm not. There we are. All right. This is our JACOBI solver. It's running in MATLAB. It's designed to solve a steady state problem. So it's exactly the same as your challenge problem, but this is for the 1D bar problem. For 1D bar, the A matrix is actually very, very easy. All of the diagonal terms are 2. We had -1 on the off-diagonal terms. For the unsteady problem, for the steady problem we were looking at, we had to set the temperatures on the left and right-hand bounds. All we had to do was change the first temperature to be 1. JACOBI looks like this. So we set the number of steps, how many steps we want to run, and then we perform these nested for loops. Basically, you're summing up A of ij times T of j. And you take that sum, you subtract it away from B, and then you divide that by AII. And that's your solution. And you keep doing that over and over again. And that's JACOBI. Oh, yes. I'll run it for you. I'll use FreeMat. That's the JACOBI solution after 10 iterations. Does it look like the FTCS solution after 10 iterations? It doesn't look exactly the same because it's bumpy. The bumpy is not a technical term. You won't find that description in the textbook. But it looks a bit like your FTCS solution. Let's run JACOBI longer. So I just ran JACOBI 10 steps. Let's change that to 100 steps. Yeah, let's do it. 100 steps of JACOBI. Let's see what the answer looks like then. Isn't that like 100 steps of FTCS? The solution is evolving just like the unsteady FTCS solution evolved. This is a steady solution. We're taking the A matrix and B matrix for the steady problem. But as we're using JACOBI to iterate the solution, the temperature profile evolves just like FTCS profile did. So for JACOBI to converge to the correct solution, we need to take the same number of time steps as we required for the FTCS. I hope this converges. It's going to converge tomorrow. FYI, FreeMat is slower than MATLAB. Okay, I've had enough waiting. We're just going to assume it worked. It's crashed. All right. So if anyone wants to have a look at my MATLAB code for JACOBI, you can come to my computer and have a look. I'll give you the MATLAB code. Actually, we can put it on. Yeah. And then you can write your C version of JACOBI if you want. My advice to you would be to write the CG solver. If you want to start writing a CG solver in MATLAB, or click in Ichizor, and we'll start writing it ourselves by hand. All right, go for it. You need to build your A matrix first, so don't even start trying to do CG until you get your A matrix done. Good luck. All right.
The matrix part is defined.
Yeah.